Hello everyone, I'm Chris McIntosh. I help teach the statistics courses. This week I wanted to emphasize a few points about simple regression from the Navarro readings. This is coming from chapter 12 on correlation and linear regression. I left this slide in here about correlation. Correlation allows you to quantify the strength and direction of the relationship between two continuous variables. And you're basically answering the question, what is the direction and strength of the relationship between the two variables? To make predictions, we need to know more than just the relationship between the variables. From math class, probably a long time ago for most of you, to graph a line and calculate the value of one variable with another, we need to know the intercept and the slope. And in the US, the format for that equation that we use is y equals mx plus b. If you were educated outside the US, then I think you see another form of that equation, but it's similar, has the same parts. Y is the outcome variable, x is the input variable, m is the change in y with respect to x, and b is the intercept. And we often call m the slope. We need to know the same information for regression, but we write the equation differently. So that equation is pronounced y hat is equal to b naught plus b1x. Y hat is the predicted value of the outcome variable. X is the independent variable. B1 is the slope of the regression line for the independent variable. And B0 or B naught is the slope. I wrote that wrong on the slide. Let's fix that while I'm here. B naught or B0 is the intercept for the equation. Let me just find that and fix it. Okay. Linear regression minimizes the distance between the regression line and the data to do the estimation. This type of estimation is called ordinary least squares estimation, and this is called ordinary least squares regression. And this illustration came from the Navarro text. The line on the left runs through the middle of the data, and if you looked at the distances between all the data points and the predicted values on the line, then they would be less than the distances between the illustration on the right. The overall fit of a regression model is evaluated, and we do that in a couple ways. One is we look at the coefficient of determination, and the coefficient of determination is called big R squared, and previously we looked at that with, I'm going to fix this, squared. Let's make that a superscript. So we looked at this with correlation, and it's the percent of variance shared between the predictor variables and the outcome variable. And this is all I'm going to say about this week, and we'll talk a little bit more about it next week. But if you run a correlation between this predictor and outcome variable for a simple regression, you'll see that the big R squared and the little r squared are going to equal each other. We'll see how that changes next week. But it's basically the same thing. We also do a significance test for the model, and we compare the null model with the model that includes the predictors. So the null model in this case is a model that just has the intercept, and the null hypothesis is there's no difference between the null model and the model with the predictors. An alternative hypothesis is there is a difference between the null model and the model with the predictors. And we get an F value for that, and a large F value means we have a significant difference. That'll give us a small P value, and that indicates that our model performs better than just the null model alone. Check test assumptions before interpreting results. We have the same assumptions we had for Pearson correlation. We want to check normality for our variables, and we want a continuous outcome variable. This is a little bit different. The predictor can be any level of measurement. So we're only going to go over a continuous variable example, but there is a way to use categorical variables in linear regression. We won't go over it, but just be aware that that can be done. We have the sample is randomly selected from the population. Variables have a linear relationship. Observations are independent from each other, and we still have our homoscedasticity assumption, which is that as one variable increases, the spread of the other variable around that point in the line are going to be similar. I left the scatter plot for homoscedasticity slide in here just to remind you what that was. You see at the low end for X, these dots are pretty close to the line, and at the high end of X, they spread out a lot. So that's heteroscedasticity, or when we're violating our homoscedasticity assumption. You'll just want to be transparent when you run into this situation and just report it with the results that there was a problem with that assumption. And we're going to go through the steps for conducting a simple regression in the computer assignment. The one notable difference you're going to see is our NHST steps with our four-step process: state the null and alternative, establish criteria for rejection, calculate the test statistic, and make a decision about the null. We actually do that 2 times with regression. We do it 1 time for the model overall, and we do it 1 time looking at the parameters, and we're going to see what that looks like. But for all regression analyses, you're going to go through this kind of 2-step process, looking at the model overall and then the parameters separately as part of that analysis process. I wanted to point out some issues in the Hevy lecture and just make you aware of them so you can, I guess, ignore or take with a grain of salt what is said at these points in the lecture. So in time index 50 seconds to 1 minute and 15 seconds, Hevy calls the linear regression the relationship between a single outcome variable and a single predictor. This is what I was trained to call a simple regression. In my experience, linear regression is just a general term talking about regression analyses that have a single continuous outcome, and you're using this ordinary least squares estimation method. That's just generally linear regression, and it's not really specific that it's a single predictor variable or if there's more than one predictor variable. We're going to see that next week, and so just be aware that I was trained to call that simple regression, and this term linear regression, I don't think that is specific as she makes it out to be in the lecture. And then in time index 335 to 5 minutes, Hevy calls the B values the beta values. In SPSS output, B values are the unstandardized parameter values, and beta values are the standardized parameter values. What Hevy says in the lecture about the beta values being the unstandardized values is incorrect. And you can see the SPS output on the page, and I meant to put that page number in here, and I can get that in here. That was page 188 in your text. Also, at time index 8 minutes and 40 seconds to 8 minutes and 58 seconds. She reiterates this and states it again. And SPSS, and when I used it, and apparently currently, because this is what she was giving, the B values are the unstandardized parameter estimates, and the beta values are the standardized parameter estimates. However, I have seen published papers that use the word beta for unstandardized estimates. And it took me a little by surprise because of I was trained using SPSS, and so I was used to the B's being the unstandardized estimates and the betas being the standardized estimates. So I don't know if that's different for other statistical software. I checked in R, and they don't use that B and beta convention. They just give you estimates for the parameters, and we'll see that the Genome does the same thing. They just call it an unstandardized and a standardized estimate. So I guess disregard what Hevie says there. That doesn't match SPSS, what she's using. And then apparently on 192, Hevie has some another table, and you'll see that the unstandardized and standardized coefficients and B's and betas are listed correctly in the textbook there. So disregard those parts of the lectures. Hevie on page 188, there's an actual error in Hevie's textbook, and that is the standardized coefficient heading that's in the third column over. She put that in the wrong place. That should be on the fourth column over. And the value of 0.913, she put that on the constant row, and that actually in the beta column, and that actually should be on the BLL parameter row, one row down. When you standardize the variable, you switch the mean to 0 and the standard deviation to 1. That means that the constant is the intercept, and that's the mean of our outcome variable when our predictor variable is 0. So the standardized intercept is always 0. So that cell should have just been left blank in the table in the text. So just be aware of those two mistakes in that table on page 188. All right, that's all I wanted to go over with you for this lecture, and I will talk to you guys later.